Or good morning to all the people who are joining in the International NASA Space Apps Challenge this weekend. We are at the finale point, and what a great finale it has been, and all the hard work has been done. You know, I have to think in this building, this awe-inspiring building, 57 years ago, President Kennedy threw down the gauntlet and asked us to why we choose to go to the moon in this decade and do other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and the skills, because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win. I think this weekend's Space Apps Challenge embodies that. 57 years ago, he said that in September of 1962. Think about it. In 1969, on July the 20th, we walked on the moon. What an incredible challenge. And what an incredible night to be here in Huntsville, Alabama, which I truly believe is where the moonshot was made. And to all of you joining us from around the world and other cities throughout the U.S., you are as inspirational as well as we go forward. So thank you for joining us. Thank you for being here. And I want to turn it over now to Sierra Elledge from the Urban Engine.
I'm clearly like 2 foot shorter than Dennis. So good evening, I'm Sierra Elledge, and I'm the Community Engagement Director for Urban Engine, and we are blessed with this opportunity to be the facilitator for Space Apps Huntsville. Our mission at Urban Engine is to propel Alabama's economy forward by connecting aspiring entrepreneurs to established business leaders, educational resources, talent, and community. So the NASA International Space Apps Challenge is one of those ways that we put this mission in action. So over the last 2.5 days, you guys have created pathways for innovation that lead to outcomes of new business, new jobs, more young people inspired to pursue careers in STEM, and facilitated revolutionary technology through collaboration, problem solving, and working together as a team. Just a small example of that impact is Jonathan Roswag. Last year's Space Apps Challenge helped launch his small startup business into the world of government research with just a quick coffee chat with some NASA employees at our event here in Huntsville. That ended up with the opportunity to do research and development for Marshall Space Flight Center and had to hire 2 additional employees to help complete the task. So what did he do? He reached out to other high school participants who had just graduated because he knew that they had the skills that he needed because he mentored them at the Space Apps Challenge. Those students expressed afterwards that having that career building experience helped them better contextualize the kind of work they loved doing and what skills they truly needed to advance their careers. None of this magic would be possible without our sponsors, so I'd like to thank Intuitive Research and Technology Corporation, Lockheed Martin, the University of Alabama Huntsville's I2C under the leadership of Rigbed Joshi, Maynard Cooper and Gale, Warren Averett, and the U.S. Space and Rocket Center, Bastion Technologies, Flourish, Northrop Grumman, and last but certainly not least, our generous prize sponsor and amazing partnership that we have with Huntsville Steamworks. We do not only appreciate your commitment to Space Apps Huntsville, but also your investment in the future of technology and innovation here in the Rocket City. Thank you also to our participants. Do not think of today as the end of this project, but the beginning, no matter the outcome. Urban Engine and our many supporters are working hard because we believe in the potential of each and every one of you and what you can achieve if you make the effort and stay diligent in the pursuit of your dreams. We would love to see you at Co-working Night on Wednesday nights, putting in the work to expand your knowledge and skyrocket your success. Each of you has the ability to succeed if you just keep moving forward. Finish this weekend's program is just a huge sign that you can and will achieve greatness. I would also like to take a moment to thank the volunteers, mentors, and speakers who committed their time, energy, and talent to make this weekend a success and inspire greatness in these participants. I would also like to take a second to recognize all of the members of our Space Apps Planning Committee who have dedicated countless hours over the last few months. If you could stand up when I call your name so we can recognize you. Matt Brooks. Andrew Denio. Matt Jones. Emily Mendez. Logan Moore. Jonathan Heath. Shay Lamond. Nathan Close. Michael Carroll. And Tony Eberhardt. Thank you so much to our fabulous MC, Dennis Leonard from the EDPA. He drove all the way from Birmingham to be here each day with us this weekend, and he breathed so much life and energy into our weekend and into our participants in the global live stream, and you have been an absolute joy to work with this year. Thank you to our friends at Workbay who've been here supporting us and supporting our global live stream and jumped on the chance to come all the way to the United States again to be a part of this event this weekend. You've been invaluable in capturing this content to educate for years to come, and we really appreciate you. We can clap for them too. I also want to say thank you to our volunteers here today from Theater Huntsville for helping this sleep-deprived and absolutely exhausted team run the show today. I am 99% sure that I am sleepwalking right now. Last but not least, thank you to the Global Organizing Team and Science Mission Directorate. Yeah, you guys stand too, all of you. It has been an honor to represent Huntsville as the main stage, and we really appreciate your confidence in what we're able to do here. So, all of that rambling and thank yous, now's the part that you guys have actually been waiting for. So, I'm happy to announce our finalists for the 2019 NASA Space Apps Challenge. If you guys would stand for some applause when I call your name, but then sit back down, I'll have some instructions for you afterwards, if that's okay. All right, so in high school, are you guys ready? Are you excited? Where's all our high school participants? I said, where's all our high school participants? Okay, there we go. I was like, there has to be more than 1.5 of you. Okay, so our finalists in high school, Team Cyber Sisters. Awesome. Forensics. Are you guys here? Awesome. And then Team Beachy Clean. You guys here? Back there in the back. Awesome. Okay. And then in our open division, which consists of college age and professionals, populated risk. Are you guys here? Yeah? Okay, great. The Wet Bandits. Awesome. And then we have Punks Unlimited. Are you guys here? Maybe? What's that? We have, it's not on here. Starstruck? Okay, sorry, we had a tie for that, so there's actually 7 teams. I'm sorry, it wasn't on my sheet. We have a tie, and we also have Starstruck. Are you guys here? Awesome. Okay. So if we could have the high school teams, please stage over here with our volunteers and to prepare to present. And then when you're finished, the college and professionals will do the same. So good luck to our teams. While they're getting ready, I would like to let you guys know about how the judging process goes. So each of our teams will come up on stage and they will have a 5-minute period to complete a pitch. And then there will be time for question and answers from the judges right after that. And then judges will be evaluating the teams based on impact, creativity, complexity, and presentation. So good luck to all of our teams.
Right now.
With such strength and poise. Or sometimes if you swipe this way, it works. Don't do that, because it might clear it.
This is okay. We'll hold down the FAQ.
Hey, here's the mic. The mic's on.
Okay, so that just.
You ready? Okay. I will be you're not ready yet. Okay.
Right. Also let them know that if they're not a finalist, they still need to hang out and wait because we still have lots of prize money to be developed.
There's one piece of housekeeping I forgot to mention in my opening remarks. If you're trying to get on the Verizon network, please don't. We need that bandwidth for our team, our communications team over there, and our streaming team. So please try to stay away from the Verizon network. You ready?
Oh, we got it. We got it. All right.
Okay.
Would y'all like to introduce yourselves? Okay.
All right, ladies, you ready to go? Keep in mind you have 5 minutes, and I will give you a cue when you're getting close to those 5 minutes to know that you need to wrap it up. All right, please start.
Hi, I'm Ella Dewis, and I'm representing my team, Cyber Sisters, which is also my JROTC team and Girl Scout troop. As Girl Scouts and JROTC cadets, we have a duty to help people, which inspired our choice of the challenge, Rise to Resilience. In this challenge, we are green engineers creating a tool to suggest changes to lessen the effects of drought and unsustainable land use. Both of these problems pose immediate and long-term threats to humankind and the earth. On a smaller scale, California is dramatically affected. Plants are dying, 1 million people must drink unsafe water, and poor land use is permanently ruining and scarring the land. 15% of ecosystems such as chaparrals are increasingly dry and susceptible to fires. Clearly, there's a large problem, and many communities are still ill-informed and underprepared. The solution is LSAP, or the Land Sustainability Action Plan. It starts with an assessment for towns' governments, which categorizes into types of droughts like agricultural, hydrological, or meteorological. Then it goes into questions about the water system and follows up with questions about land use and transportation sustainability. For each question and category, the program formulates a custom action plan to address the problems on all levels, immediate and long-term. Another great feature of this is every report includes information on how these changes can produce profit and bolster the local economy. The result is a comprehensive, multidimensional, achievable procedure with strategies to lessen the effects, put in place temporary measures, and institute long-term practices. We put this on our website of the same name, LSAP, which also includes resources for community governments and citizens, like the contact page, which has regular and emergency services about drought and land use. We also made a mock-up of layered data with flood regularity and groundwater depletion. We would use layered data maps to keep the public informed, and it also achieves the double purpose of keeping them active in the solutions the assessment recommends. LSAP has many more specific pros. The wide range from urban to rural communities in California has often made creating solutions more difficult in the past, but because of the categorization system and the range of questions, LSAP overcomes that obstacle. Another common roadblock is the cost of making green modifications, but the plan accounts for that through the economic section. The benefits of improved agriculture, job creation, and money saved on water makes up the cost, along with preserving a fair cost for resources in the future. The website also has multiple purposes and resources, which is advantageous to the users of LSAP because they get more out of it. Part of the reason we're so excited about this project is that it can be easily added onto and made more detailed. With more time, we would put our website on the internet as opposed to a local host and create and expand our layered data maps. In the big picture, we would expand to include other problems like wildfire prevention, and expanding renewable resources. We'd also expand across the country and possibly even the world. Today, we hope we have shared with you a new solution for the most pressing environmental problems we are facing today. As we like to say, LSAP, ASAP. Thank you. Do you want to do the demonstration?
Can you say something about it?
Yep. We are going to very quickly demonstrate our questionnaire and what the action plan would look like to the judges. Yeah.
You have 20 seconds.
These are the screenshots of our website, so you can see that it looks pretty nice for about 24 hours.
Time is up, sisters.
All right, thank you. Yeah, I believe they asked.
The judges now have 2 minutes to ask questions. Carrie.
Where are you pulling the data to include your economic information?
So we actually spoke to an economist at the facility, and we also pulled it from the Pacific Institute research profile on it. I can actually pull it back up. These are the two data tables we used mostly.
Thank you.
I have a quick question. What were you trying to show us right now?
So we are trying. I was trying to show you the assessment of that Ella talked about, and so when she was talking about asking you the questions and trying to find out what kind of drought you have and sustainable land use. Does that answer your question?
So was that a piece of code that you were trying to show us?
Yes.
Okay, thank you.
You're welcome.
Any other questions? Okay, thank you very much.
Yeah, we had a lot more last year. It's all right.
So I'm going to ask the judges a couple of questions while we're waiting for the next team to set up. Carrie Freeman, you may have come the furthest distance to participate this weekend. So you're from Spaceport in New Mexico, right?
Close. I'm from Second Muse, but I am based in New Mexico.
Okay.
Where we do have a spaceport.
Okay. Explain why you feel this is important.
So I'm with a company called Second Muse. We've been part of the global organizing team for SpaceApp since its inception. And really our ambition in the world is to bring about the collective genius to build the future economies that we want, those that are sustainable and inclusive and circular. And so to us, this is like absolutely core to everything that we do. So we're really proud to be here.
That is a great answer. It's absolutely core. And it really is about future building. Thank you so much. Tiffany, while we're waiting for the next team, real quickly, what would you like to see in the future from a space perspective?
I just want these children to feel empowered to bring their ideas to life. And I'm really glad to be a part of the judges panel, and I'm really glad to see Urban Engine do that. What do I want to see in the future? I have a whole bunch of visions.
Thank you so much. How are we doing, guys?
Yeah.
Ready?
Okay, we're good to go. Hey, guys.
Are you ready? Pitch away.
Sure. Hi, everyone. Good evening. My name is Annika Pant. I'm joined by my partners Katsuki Chen and Viraj Kakkar. We're representing the Forensics team. Today, we're very excited to present our work on the Famine Risk Index Early Detection System. Over the last 24 hours, we built a platform for elucidating the relationship between drought and population at risk via an interactive user interface with a focus on ease of use. So the motivation behind the project centers around humanitarian aid. We need to help identify populations at immediate risk from famine. In fact, the WHO quotes that 35% of deaths and disease are related to undernourishment in sub-Saharan Africa. In this project, we actually chose to study the African region using satellite imagery. Additionally, with this project, we look to study the consequence of drought on famine and help those who need aid get it quickly. The problem we looked to solve this weekend, in our background research, we saw a lot of preliminary indexes, but could not find any that combined the effect of drought and immediate environmental hazards with mortality rates and demographics, etc. For example, the UN's Global Hunger Index, or GHI, neglects environmental hazards completely. Data sources, additionally, from the UN are withheld and are limited, so we saw this challenge as an extremely awesome way to remediate this limitation. So this weekend, our solution looks to pose an intuitive and interactive visualization for identifying at-risk populations. We look to identify at-risk populations using our Famine Risk Index, or FRI, and we look to consider rainfall, vegetation abundance, and population density of local areas at a very high resolution using NASA satellite imagery.
So behind me, you can see the formula that we developed for calculating our famine risk index. And we collected this data based on population density, rainfall, and NDVI, which is a vegetation index. So by calculating a t-statistic, we are able to locate the significant anomalies that the RFI tells us, which represent high risk for famine. And Viraj is going to talk about those next.
Can you get help, please? Ziffer.
We have stopped the time so that you will be able to catch back up. I assume this is your team mascot.
That's correct.
Yes, sir.
Okay.
Start.
So here you see our interactive dashboard. We utilize an open source framework known as Kepler-Geo, which is powered by WebGeo. And in this plot, we have over 203,000 data points plotted here in real time with low latency. So at first, you can see there's a variety of color. This is our heat map of our FRI. The darker this color is, the higher our FRI is, indicating that there's a higher risk. Now, at first, you may see that this data is a little bit hard to see. And as a scientist, I can understand I'd want to select certain areas or percentiles. Here, we can actually change our percentile for average FRI, allowing more interactivity in our dashboards for scientists to utilize in developing any story or case study they wish to look at. In addition, we also want to look at environmental causes and different demographic causes over here. So we can go over here, and we have various options we can choose from, NDVI or rainfall. Here we have rainfall. Our height is the concentration of rainfall in an area, and our color indicates the FRI index. If I was to move this percentile to be lower, we can see there's going to be a little bit darker, indicating that there's a higher famine risk index.
So to conclude, over this weekend, we developed an interactive dashboard for studying the relationship between drought, rainfall, and vegetation with risk in famine conditions. We hope you like the project. Thank you very much. And we'd be open for questions.
Thank you. Judges, you have 2 minutes.
So I have a quick comment. Firstly, fantastic presentation. I think you were able to capture the problem and drive the solution and explain what exactly you were able to achieve in this hackathon. So well done. And
Thank you.
There was no guesswork in terms of what you were trying to explain to us today. So fantastic job.
Thank you.
All right, I'll continue on with the economic theme. All the data sets that you pulled in are really looking at things, and from what I can tell, not including a socioeconomic element. Is that something that you would add, or how would you actually factor that into your risk?
This is a very fantastic observation and is a limitation of our current model. Now, obviously, we're only considering population density at the moment. One problem that comes with including socioeconomic data, and this is a problem, a limitation that we encountered during this weekend and would love to find a way to overcome, is that due to the nature of some socioeconomic indicators, the resolution of this data is on a much less fine level than the satellite imagery provided to us by NASA. And so when we do something like that, we lose this population refined resolution to be able to identify exact populations in our data, but that would, of course, serve as a very useful indicator. We would love to include this in a future study.
Were you able to go backwards and correlate any of the data that your model tells you should indicate an enhanced famine risk with actual famines or with other developments that have led toward famine?
I'm really sorry. Could you repeat your question?
Sure. When you look at the scores your model produces for famine risk, have you been able to correlate that with past famines in any way?
Yes. So for example, actually, in this visualization here, you can actually see that as expected, as the as the population's average rainfall decreases, the risk for famine increases. And this is likely correlated to a large percentage of agriculture for subsistence in southern Africa. And you can actually see this being elucidated very clearly in our visualization.
Time is up. Thank you very much.
Thank you.
Paul Rocho, explain to the audience here, both here and globally, the importance you feel of continued exploration, not only in space, but what it can do for planet Earth.
So I grew up watching NASA do amazing things. We put humans on the moon. We put humans into orbit for long-term scientific research. We greatly broadened crewed spaceflight. And the things that we've learned from that have just been astonishing from a scientific perspective, from a medical perspective, from an economic development perspective. There is so much out there. I think it was Larry Niven, the famous science fiction writer, who said that essentially, when you think about the resources that are available in space, it's raining soup, and we can make buckets. There is so much for us to learn and explore in near Earth orbit and throughout our solar system that I'm delighted to see that we're starting to recapitalize that exploration and to capitalize on the things that are out there waiting for us to find.
Great. Thank you so much, Paul. Do you guys have a presentation deck? You do not. One quick question. Is Punks Unlimited here? That is the next team up. Oh, that's so punk-like not to show up on time. Okay, take it away.
Hello, everyone. I am Seamus Higgins.
I'm Ruby Shepard.
And I'm Jacob Copeland.
We are Team Beachy Clean, and we're representing New Century Technology High School. First, I'd like to address our problem. As many people know, trash can enter pollution in very physical forms with stuff such as water bottles, plastic bags. A lot of that waste can end up in the ocean. And the current issue is, how do we tackle this without harming the environment that's already there? We've come up with a solution that we believe can help in many different ways. We call this, very lovingly, the trash whale. The reason we call this the way it is because it combines a lot of drone technology and biomimicry. First of all, I would like to talk about the drone technology. We discussed a lot of ways to handle this, and I think the most important way is that this device would be connected to a central server located virtually anywhere, either on some sort of fishing boat out on the ocean, local homes, near ponds. We wanted this to be primarily used for the ocean, but we wanted it to be adaptable not only to other oceans such as the Arctic or Pacific, but we also wanted it to be potentially usable in areas such as ponds, areas such as China where pollution can flood local lakes and ponds and cannot be usable and can often lead to a lack of vegetation. The trash whales primarily used through drone technology. I apologize, we did not prepare a very strong presentation as presented. What does it do? Good question. The way it obtains trash is through our model here. We have it separated by color, and this is unfortunately not the scale. The central body here is held with a mouth here that is designed to open and shut at will in order to prevent trash which enters this body here to not fall out from movement as it's propelled by this fan. Electronics are also held in there for stuff like GPS to send back to that central server and release information such as we plan to have sensors in there where it uses thermal and sonar to detect such as wildlife, where if this did enter wildlife, there is a potential for it to harm, but if we simply know where the wildlife is and work around that, it's a lot easier to deal with. It enters the mouth. As it propels forward, it enters the mouth and is moved up by a conveyor belt into the body. The body is, the bottom of it is filled with a mixture of, we weren't quite sure of the term, a mixture of cylinders that would be loosely held in order for water to fall through without allowing the trash to fall through itself. We went through a lot of different ideas and movements, and ultimately we are very proud with the one we have, as it has gotten us this far somehow.
Thank you so much. Judges, you have 2 minutes.
So I have a question. Have you thought about how you would power this device?
We primarily plan to use battery power, as this is not only just one, but it's multiple, which is why we also use the central server, as anyone with a central server and one of these, maybe 2, 3, 4, it's designed to be used by almost everyone and anyone.
I have a question. Do you envision this working as like a mesh of intercommunicating devices, or are they going to communicate back to a central unit on a boat, as you said, or are they going to have a central unit that goes with like a swarm of those things so that they maintain some central distance or diameter to a central node, and then that node communicates back, or do each of them communicate back?
Each of them would communicate back using GPS back to one central server. The central server, the drones themselves are much more of an extension of the central server rather than their own individuals.
Is it limited to the type of trash that it's going to pick up?
Primarily surface level trash, but this can often lead up, and this is merely a part of the whole solution, but surface layer trash can oftentimes be one of the easiest things to clean up without doing too much to the environment itself.
I have another question. You said that this was not to scale, was not the correct
Yes.
size. What do you see as the correct size?
The correct scale would roughly be, we've color-coded it. These are our flotation devices, which would keep it buoyant. These would about be the size of the body. The mouth would have to extend outward, and the conveyor belt would still be flat, but those outer ends would stick out. I'm sorry, it's very difficult to just explain this off the top of my head.
So the totals, is that
Time is
represent-
up. I'm sorry. Sorry, Susan. Thank you.
Yes, we could.
So we're waiting for the next team? Okay, while we're waiting, Rigvid, you've got a few seconds for an elevator pitch on the I2C and its importance this weekend to the International Space Apps Challenge.
Well, what a great question, and thank you so much for asking that question, because we are extremely happy to partner with Urban Engine for this event. I2C is an initiative that supports entrepreneurship, that supports innovation, supports new businesses and startups in the technology space. And what better way for us to show that we really care about this community as it relates to helping companies, helping students learn about, get educated about starting new companies. So I think just being able to collaborate with organizations like Urban Engine, coupled with the resources that we provide startups and we provide entrepreneurs, I think is a great value add to folks who are looking to ideate and folks who are looking to scale their businesses. So
that's great. Thank you, and thank you for coming to Huntsville. You've only been here a few months, right?
I've been here since 2017, but we opened doors to I2C in June.
Well, thank you so much. You're welcome. All right, we're ready now for the college and professional side. We're waiting on your deck to get up, please. While we're waiting on this, judges, how long did it take to get the live signal from the moon back to Earth and mission control? Any idea? The answer is 3 seconds. Kind of an amazing feat within its own right. You guys ready?
Okay.
Rocket.
All right, so we're Team Populated Risk. My name is Ankur Shah. This is Viraj Sanghvi, and we created a mapping tool that maps the most vulnerable populations to natural disasters and included socioeconomic variability within that analysis. So I'm going to show the video we made and then talk about, show a live demo of the tool. Our team is Populated Risk, and we're tackling the Curious Minds to Helping Hands challenge. Natural disasters such as cyclones, droughts, and floods are becoming increasingly frequent and severe as a result of a changing climate. In the past 20 years, disasters cost more than $2 trillion and impacted more than 4.4 billion people. However, these effects are disproportionate. A high number of women, children, and people in poverty are the most impacted, but we don't fully understand these vulnerabilities until it's too late. This is why we created PopRisk, to combine disaster data with social vulnerability data to create visual and statistical actionable insights into populations who are most at risk. We developed a web app using .NET at Mapbox.js to create map styles and layers to display multiple datasets. The hazards layer on the map include the location of active fires over the past 48 hours from MODIS, near real-time earthquake alerts, and landslide susceptibility from NASA's global landslide model. Our unique solution to the problem was using Social Vulnerability Index from CDC for the U.S., which is calculated using data on socioeconomic status, disabilities, minority status, and access to transport. We will use this data to find specific population groups by age, gender, and income who are most affected by a specific environmental disaster. In the future, we hope to visualize forecasts of hazards and affected populations so we can mitigate hazards before they become a disaster. Okay, so the idea here is to create, we created a subset of what is possible. But the future plan is to make this available to local, regional humanitarian aid organizations. So if information on the most vulnerable populations by age, gender, poverty comes to the local government officials and NGOs, they can be more active and optimized rescue efforts. So I'll let Viraj show a live demo of what this tool is about.
So I started by making a .NET application, a web app, and so I'm going through and using Mapbox to plot active fires, CDC, SVI data, social vulnerability index, live earthquakes, and and NGOs in order for humanitarian officers of governments, government officials, UN officials who require these this sort of information to make decision. So a lot of these points are based on the UN document that we read, which was about gathering specific SVI indicators that we're plotting, and this is the tool and the ultimate result of that.
Yeah, so one of the issues we ran into, in fact, we ran into many issues, but one of the main ones was SVI is very well defined for the US. So CDC has a formula for calculating SVI. It's based on 4 different factors, as you saw in the video. But SVI is not defined for places that need it the most, like Africa or Middle East or even Southeast Asia. There is no SVI data that we could find. So one of the tasks, if this becomes successful, is to gather or create SVI data for these regions. And the plan is to focus on specific regional disasters. For example, California, it'll be drought, or Japan, it'll be tsunamis. We want to focus on specific disasters for specific regions and have SVI for each country. And this will be a global project. So that's what we envision if we take this forward. All right, that's our time. Thank you.
Thank you. Paul Livingston Stanberry, what would you like to ask them?
So my question is, how do you balance out the different kinds of data you've got? Some data may override some other data, possibly.
So SVI accounts for a lot. So SVI, that is a very good point. SVI accounts for a lot of those hazards that we mentioned, like the risk for a particular area to go through a catastrophic hurricane or tornadoes or whatnot. All of that's accounted, but like in every other, known fact in statistics is the more you add data to a statistical formula, the generalized each individual random variable becomes. So those things are not as magnified when you take into account all of that information all at once. So you want to take it piece by piece. You want to take the generalized version of it, and you want to take the more specific version of it. So SVI would be the generic total, like the total number, that's like how vulnerable someone is, compared to the specific disaster that they would go through. So that was the main idea.
Time for one more question.
If you could pick any data source to add to make this a better model, what would you pick and why?
That's a very good idea.
I would say global SVI data, because the United States is in a better position to gather data such as the SVI. SVI is very complex. It requires a lot of different variables that you need to collect. Most governments don't have that power to do, gather that data. So luckily, US does. But I would say global SVI data would be amazing.
So along those lines, I would love to just suggest and recommend you, along with Cyber Sisters and Forensics, actually connect with the World Bank as well as the GFDRR organization, so the Global Facility for Reduction and Risk Recovery.
Okay.
It is housed in the World Bank in Washington, D.C., but they're the largest global organization that's working to solve for this, and they haven't done it yet.
Great.
So
Thank you.
Thank you so much.
Time is up. Next team. So Susan.
Yes.
Let me ask you a question. Susan Spencer. As this team is getting prepared, and this is a big team, they've got all kinds of show and tell. What is impressive about this weekend of Space App Challengers that you've seen?
The most impressive thing is the change in perspective that young people have today. When I was young, everyone in this town was involved in the space development program in the 60s, but we grew up thinking that. Everyone thought big. And then we got out into the world, and that wasn't true. But now everybody is starting to think big. Everybody believes that they need to bring their talents to solve the world's problems, which I think is a huge, huge change in how how the world is developing socially, and especially programs like this bring an opportunity for people to bring their talents and show that the world is is open. The space is open to everyone. So it's really, to me, it's kind of a maturity for people to show this level of maturity at this age is a wonderful thing, which again, we haven't seen for several a couple of generations. When I was young, we didn't have that at all. So
Great answer. All right, you guys ready?
Sure.
Take it away.
All right, so we're the Wet Bandits, which is a Home Alone reference, by the way. Yeah. So we're a group of engineering students from UAH. I'll do really quick introductions. I'm Sean. That's also Sean. We got Fred, Thomas, and Colin. We got a bunch of MAEs, and then Sean and I are ECEs. So we came into this hackathon we kind of wanted to build something hardware related. And so really we were constrained by what we could gather. Big thanks to the Space Hardware Club for letting us steal a few components from their lab. And then also we used this rover that we have in Thomas's senior design project. And so when we approached the problem, we tried to figure out within those constraints what challenge we could do, and then what also we could do within that challenge with the things that we had. And so I guess the major things that we have of course have the RC car. We have, along with that, a PixHawk controller on the RC car. We have a Raspberry Pi and an ultrasonic sensor as well. And those were kind of we had like a couple of other components to work with, but those were the main things that we had to design our project around. And so the challenge that we chose with the eensy-meensy tiny sample one, which was being able to choose a sample or determine what to sample on the moon's surface. And so I'll let Thomas talk about that a little bit.
So part of the challenge was to identify what the valuable substance on the moon would be to sample, and we chose ice. Since that's kind of where lunar colonization is going, is to where the ice is. So NASA currently has radar maps that project where the ice relatively is, and our rover here is actually a scout rover that would pick out the exact locations of the ice using, in this case, our ultrasonic sensor was what we demoed it with.
So we'll talk about this. So the ultrasonic sensor that we used is a basic Arduino one. The premise behind it is if you hold it at a certain distance, because generally these sensors are used to measure distance, you can determine the different densities of the material you're measuring. So in this case, ice would give us a much different value than something like sand or dirt or carpet or whatever we were measuring at the time. So this is our video of our proof of concept testing to make sure we could do what we wanted to do.
Yep. As far as the mechanical loadout goes, we mostly had what we had to work with. We used a Cheez-It box, a shipping part, we used a bunch of rubber bands, a bunch of power sources we had lying around. We had to wrap the whole thing in plastic wrap because it was sprinkling half the time we were out there, which is kind of brutal. But mostly we had to do a lot of configurations because we just had the base drone and it wasn't optimized. We had to make sure it could turn right, it could carry the loads we put on it, make sure it could operate decently on our in Earth, just to make sure it could work on the moon or anywhere else. And yeah, he'll be passing it over to the judges right now. It's not the prettiest, got a lot of wires sticking out and everywhere, but it did the job. We could drive it around, we could use then GPS data to move it around all over the parking lots.
So this is the video of us actually being able to detect ice. So what happens is the ultrasonic sensor, you can't see it on the video, but there's two little holes in the front of it. And what happens is as it drives over ice here, you see this blue LED light up, and that basically says we found ice. And everywhere else that we haven't found ice, it doesn't light up. It's the basic principle here. And moving forward, we were able to autonomously control this using our software here. This is a COTS software. It's able to just put waypoints on a map and a GPS, and it'll follow that waypoints. So what we did was we integrated with that with our Raspberry Pi, and we were able to tell whenever we weren't moving to actually start collecting data, because we couldn't really collect data on the move. And once we stopped, we collected our data at our waypoint, wherever the ice would be, or we would hope it would be, and we would be able to say, okay, we have ice here, we don't. And then we were able to write that GPS point out as a data file for future analysis.
And so moving forward, what will happen is, let's say this actually goes to the moon, right? Ultrasonic sensors don't work very well in the vacuum of space, but this is very analogous to something like a ground penetrating radar or something electromagnetic that will work on the moon. As well, obviously, again, GPS isn't really on the moon because there's no satellites flying around it. So something else would need to be implemented for there to actually be able to work on the moon in that way. But we felt that this was a very analogous system to something that could be implemented and actually sent to the moon to save valuable astronaut time of just walking around trying to find the ice.
20 seconds.
In the larger areas that the satellites have found. That's really it.
Yeah.
Great. Judges, you have 2 questions. 2 minutes, excuse me. Paul? Larry, I'm sorry.
So I'll ask the same question as before. What about how you can power the thing? How's it going to work?
So right now, we have just basically portable phone battery packs. There's like 3 of them on there, one for each system. So there's a battery for the Raspberry Pi, there's a battery for the controller and stuff like that. But on the moon, you have something like solar arrays. You can use more powerful LiPo batteries and a much better integrated system.
For the case of the moon where the ice is, it tends to be in shadowed parts of the moon. So we would actually be relying a lot on nuclear power because the solar power would only be reliant sometimes, depending on where we were in the crater.
Other questions? That's it. Thank you so much. Larry Livingston Stanberry, you're participating, you're judging, and you're a volunteer for this. What did you think you were going to get out of this today?
So what I hope we'll get out of this is some new ideas that help propel us into the next generation. Obviously, we've got a challenge ahead of us over the next 5 years to get back to the moon. What I'm hoping is that some of these folks have got some good ideas that help us get beyond that. Because without that constant evolution, we lose our place. We're going to, we can sit on our tails all day long and not get anywhere, right? We really want to get beyond, help get ourselves out and see more things.
That's great. Because it really is an incubation of ideas when you think about it. And I think that is the beauty of this Space Apps Challenge. We are really hearing wonderful ideas. While we're waiting there to log on, wouldn't you love for the leadership in the early 60s of this country to be able to come back today, sit in this room, and hear these ideas, but also visualize the tremendous achievements? Wouldn't that be an amazing thing to, I just think of President Kennedy's speech in 1962 in Rice Stadium. And I don't think he wanted to go to the moon. I think he wanted to win the space race, as I read history. But we accomplished so much more than just going to the moon. And I think that is the inspiration also. And especially this weekend, I believe that all 200 cities and countries are going to be better off as we go forward. And that, to me, is also a tremendous inspiration to keep on doing the International NASA Space Apps Challenge. You ready?
Yes, sir.
Okay.
Okay, hi guys, good evening. Our team name is Starstruck, and this weekend we had the very exciting opportunity to solve the problem of building a planet, which we did in a weekend. So we are all from UAH, and we are all computer science students. We're going to take a moment to introduce ourselves. My name is Liv.
I'm Eric.
My name's Corey.
And I'm Tristan.
So for our project solution, we created a video game, and we want to go ahead and play our submission video for you so you can get our first initial look and understand how we're going from this in terms of how our kind of project progressed. So,
Hi, we're Starstruck.
And this is Planet. With Planet, we aim to make astrophysics more approachable. We created a planet generator to fully engage the user in an educational simulation. You can navigate and inspect stars and planets to learn more about their relationships. A user interface allows you to customize your solar system. You can change your star's age, temperature, and mass. You can also personalize your planets. For example, creating a cloudless gas giant creates a noticeable blue hue. As you customize your planet, educational pop-ups inform you of how your choices have changed the planet's properties. Our goal is to encourage curiosity by creating possible planets in unvisited solar systems. By exciting others to further human space exploration means that in the future, we'll be able to get where we're going. Hint, it's probably Mars. All right, so that was kind of our initial look at our project, but we want to give you a lot more of a deeper look into what we created with a demo right now. So Eric, can you go ahead and get us started with that?
Yeah, so as you can see, we have our miniature solar system here.
In 1990, the Hubble telescope.
As you can see, we have our miniature solar system here with a star in the center and the planets orbiting around. Now, if I take a look around and I actually click on a planet, it pulls up the planet menu.
So on our planet menu, you can see a whole lot of UI going on. What we wanted to do for this was create the ability for the user to go ahead and customize their planet with different chemical compositions, changing the mass, the distance from the star, and Corey is going to tell us a bit more about that.
Awesome. So on the UI here, you can see we have a lot of different options. At the very top, you can kind of choose the type of planet you have, whether it's rocky or if it's a gas style. Eric's clicking around on the buttons on the left side. We have different choices for atmospheres, and we wanted to really represent some other planets that may exist in our galaxy. So we have the standard oxygen atmosphere as ours is, and we have things like methane and argon. And on the right side, we have different types of gas giants. At the bottom there, you can see a couple of sliders, and at the very top of it, we can kind of choose a mass. And as Eric messes with the mass, you can see the planet grows and it shrinks in the actual representation of our solar system. Beneath that, we implemented a slider to change the number of moons because moons are fun. And the very bottom, we actually chose to represent the planet's distance from the star, and that would affect its temperature as we go along.
All right, awesome. So we're also going to take a look at our star menu, which has some options too. In the star menu, you can see you can also change the mass, which will actually rescale our entire. And you can also change the age of the star as well as the temperature with the star. Also in the UI, you can see a Learn More panel, which has live links to other NASA resources, because our main goal for this game application is to get people excited about astrophysics and to make it so that they can be able to continue learning after they leave the application. Within our application too, we wanted to mention that aside from a few shaders that we pulled from open source, all of the code and all of the UI was done by us in a few hours from scratch. So, as you can tell, there are a few things that have not been implemented that we plan to implement. Tristan, can you tell us a little bit about some of those?
So, of course, when you're doing a hackathon, you're going to have some problems with code. One of the main problems we had with our code was getting the GitHub correctly set up. And so how we solved that was we basically just had a master computer that had push and pull access to GitHub, and we would just send our files over to this.
20 seconds.
And so one of the things we really mesh well as a team could be explained by Liv.
Okay, we just wanted to highlight that as a team, we all had a lot of different strengths, and that's what made us really strong and awesome on this project. So Corey does astrophysics, I do game design and UI, and
that's
art
time.
and science. So thanks so much.
Thank you. Judges, you have 2 minutes to ask questions.
What's the average age of the user?
Yeah, that's a great question. That's something that we were talking about for our audience. We're kind of looking at the gaming community as a whole. Educational games reach a lot of users, mostly from middle school to high school, but Steam, which is a place where you can kind of go and get games, has a lot of Planet Generator applications, kind of similar to this, but they're not necessarily on the same educational scale.
Next question.
Are you planning to keep working on this?
100%. We're so excited about this. Like, I want to add moons. I want to actually make it so we have a binary star in the center. So we have 2 stars orbiting around, and the planets orbit around the center of those 2. I'm so excited for it.
Yeah, we have a lot of fringe cases that Corey came up with while we were doing research that we want to implement to show people how different planets really can be in these unvisited galaxies and solar systems that we have yet to go to. So.
All right. Great job. Thank you all so much.
Thank you.
And that concludes, I believe, our presentations. Let's hear it. Can we hear a standing? Let's give a stand up for this. This is a weekending hackathon. What an awesome, awesome effort. Let's hear it. Come on, you other 199 cities and countries, stand up for this. Thank you so much. That is great. Great job, everyone. So now is my great honor to introduce Dr. Jan Davis. Even though she was born on the Space Coast, she came to her senses pretty quickly and calls the Rocket City home. Is it 873 days you spent in space? Is that right? No. More? 28 days. How many hours? Okay, there you go. It's your, anyway, she was on 3 space shuttle missions. I think it was what? 47, 60, and 85? Excellent. She's here to give us a great presentation. And I think we started off on Friday hearing from Dr. Lisa Woodson-Morgan, another astronaut who is now in charge of the lunar landing program going forward. And now we get to hear a keynote from Dr. Jan Davis. And I think it just denotes the tremendous amount of talent that we have in this community and on this country and around the world to make a difference going forward. So Dr. Davis, it's your show.
All right,
thank you so much.
I'll be ready in just a second. Sorry. Trying to load. Sorry.
Judges, you may not ask her a question. I'm sorry.
Well, hello. We're getting this set up, so I want to tell you how impressed I am with your presentations and what you've done this weekend and the fact that you spent a weekend doing these very cool things. So I'm really proud of you for doing that, and thanks to all the volunteers and judges and the people who put this together. I think it's incredible that you spent your weekend this way. There we go. So I'm wearing my astronaut shirt and my Houston Astros shirt. So I thought it was a good time to wear that since we won the American League last night. I am from Huntsville, that's my hometown, but I spent a lot of time in Houston, obviously 12 years. So what I want to talk about today, you're very bright folks out there, and I want to share with you some ideas on why we go to space. More specifically, why humans go to space. Because we have big plans for the future and we need help. And from what I've seen here, we've got a great set of problem solvers here. And so hopefully you can help us with some of these problems that we're trying to solve so that we can go explore further. So we're going to talk a little bit about that. First of all, some of my background. I'm a mechanical engineer. I actually grew up in Huntsville when we were testing this rocket, and went to the Apollo 11 launch 50 years ago. And so I was very inspired by all of that. And so I didn't immediately go to NASA because NASA wasn't hiring after the Apollo program, but I was able to go after we started getting ready for shuttle. So I started 40 years ago working for NASA. And so my background is mechanical engineering. My first degree was in bioengineering, then mechanical engineering, Georgia Tech first, then Auburn, and then I received my PhD at UAH. So I'm glad to see so many UAH students here today. So while I was at NASA in 1979 when I started was the first time they started picking women to be astronauts, and they started selecting people who were non-military folks to be astronauts. And that's when I first started thinking about it, was when I first started at NASA. And so I went back to school, UAH, and did some other things, received my pilot's license, did scuba diving in the water tank we had here to simulate doing a spacewalk. And so those are the kinds of things I thought might help me to be selected as an astronaut. And so I was interviewed in 1984. There were 5,000 applicants. They only interviewed 128 people. So I was really excited about just being interviewed. So it was a remarkable week in Houston. That's when I knew that's what I wanted to do. Had to finish my PhD, I felt like, before I could really have a good chance at it. And so I didn't make it my second time either in '85, but in 1987, I was selected to be an astronaut. So I moved from Huntsville to Houston at the Johnson Space Center. So that's kind of my background, but also the message is, but you guys have a brilliant future. And when I say guys, I mean guys and gals. I should say y'all have a great future. And so just keep at it, set your goals high. Don't let anybody tell you you can't do it, because a lot of people told me I was crazy for wanting to be an astronaut. And what if I'd listened to them? What if I'd given up after I wasn't selected? Even though I was discouraged, I kept at it. So if you don't make it the first time, whatever your goal is, or whatever milestone you have set, just keep trying, keep trying, and keep trying. You may need to tweak a little bit your goal and do something, work harder in a different direction to make that goal come true, or set a different goal. But don't give up. So, as I said, I'm going to talk about why we go to space. We have a picture up here of the space shuttle, also the Space Launch System, which is the new rocket that we're working on. There's a really nice model of it back there. So we'll talk about that a little bit too. So this is me getting ready for my third flight. And I don't look stressed out, do I? I mean, it was just great to be in space. I loved being there. I didn't have any problems with getting sick or adaptation. I just loved it. I was in my element. I loved doing the science and the engineering and representing the thousands of people who work on the space program and the scientists who put together the experiments. And it was my great fortune and opportunity to be able to represent them in space. So why do we go to space? Well, a lot of people call going to space zero gravity. It's actually not zero gravity. It's microgravity. You're in a state of free fall in the space shuttle I'm talking about. It'll be different when we go to the moon. But when you're in a state of free fall, you're still falling toward the Earth. You still have the effects of gravity, but it's like you're in an elevator and the cable got cut and you just drop. You're floating. That's what you're doing in space. You're floating in a state of free fall, but you still have gravity. But if you put a G meter in your hand, it measures zero. But I just want to make that point that you're still under the effect of gravity. So what? Well, without the effect of gravity, you can study a lot of things about science and about people and about how things work and what the basic laws of physics and engineering and science are when you take away that gravity part of the equation. So we're free falling, just as I said. We're in the space shuttle, we're free falling. That's what they're doing on the International Space Station right now. So why do we go? It's discovery. It's discovering all these different things that could help people on Earth, and they do help people on Earth, and we'll talk about that in a second. But that's the first reason we go, is to discover new things. Without the effect of gravity, there's so many things you can learn and discover, and we're still learning and we're still discovering by being in space. So let's talk about the space shuttle a little bit. Now, my first space shuttle mission was in 1992. Some of you may not be that familiar with shuttle because we stopped flying that several years ago. But it has a unique, looks like an airplane, but it's actually kind of a lifting body when it comes back down, kind of like a brick. with the effect of gravity. You don't have the engines on. But the orange fuel tank supplies the liquid oxygen, liquid hydrogen that fuels the 3 main engines that are on the space shuttle itself. And then we have the 2 solid rocket boosters on the side that provide most of the thrust. And those solid rocket boosters come off after 2 minutes. And then the external tank provides the fuel for those engines on the space shuttle for about another 6 minutes, 6.5 minutes or so. So it only takes 8.5 minutes to get into space, and we're in low Earth orbit, a couple hundred miles above the Earth. So we're not up there like the Apollo folks were, who could see the whole Earth at once. We go around the Earth every hour and a half. We're traveling 17,500 miles per hour, and that's 5 miles a second. So we're going really fast, but we don't have a view of the whole Earth. We view, just a portion of it at a time, several cities, or if you're looking at it sideways, you might be able to see a whole state at once. So that's kind of a primer on the space shuttle. These are my 3 flights. The first one was a mission with the Japanese in 1992. We had a space laboratory, which I'll show you in a minute. And then my second flight was in 1994, was a mission with the Russians right after the Soviet Union collapsed. And so that was the first time a Russian had been on the space shuttle. So it was a joint program, which really laid the foundation for us to work with them on the International Space Station. My third mission was in 1997. It was a whole bunch of different things. And we were getting ready to build the International Space Station. So we were trying out some robotics that we needed for the space station. We did a lot of science, a lot of astronomy. We deployed the Christus satellite, which I'll also show you in a minute. So this is me in space. And I'm in my element. It's a great place to work, great place to live, and to do science. Well, let's talk about the types of science that we could do up there and that we do in microgravity, which we call it microgravity, not zero gravity. So in microgravity, these are the kinds of things that we like to study because we don't have the effect of gravity. Biotechnology, combustion science. So biotechnology, I'm going to talk about in a second with protein crystal growth. Again, you can study the way cells form, the way our body behaves, the way different elements might interact, and biological elements. And so those are the kinds of things that we study in biotechnology. Combustion science. Now, if you imagine a flame, if I had a flame here, it would be a teardrop shape, right? That's because the air around the hottest part of the flame is a different density than the air at the coolest part of the flame. And that's why you have the teardrop shape. So without convection, without convection in space, the flame forms a sphere because you have that difference in density, the difference in mass, because you don't have the effect of gravity. So things are weightless, and air is weightless, and the different flames, parts of the flame are weightless. It forms a sphere around the flame. So we can learn a lot about flame propagation, what causes it, what prevents it, we can learn from it, and potentially other types of combustion that we want to learn about. Fluid physics, as you can imagine, fluids act totally differently in space. So in space, if you had any kind of liquid, like water or juice, we play with our food a lot, so we play with juice and coffee, things like that, they form a sphere. Because if you don't have gravity, you don't have something, trying to drop down to the earth and deform its shape into a teardrop shape or whatever. It just, because of the surface tension, without gravity, the physics of surface tension takes over. And so that's why, you just have a ball of liquid. So without gravity, again, you can study fluid physics in a way that you can't do on Earth. So that's something that we do a lot of experiments with. Material science, me being a mechanical engineering, this is one of my favorites. If you mix things together on the Earth, they separate out because of gravity. If you put it in a casting, like an ingot casting, the effect of the walls of the casting affect how the metal is going to form. In space, you don't have to have a cup or a casting or something to put the metal in to melt it. So we just float the metal and mix it together, and then when it solidifies, it's made a new combination of materials that we can't make on the Earth. So we combine very light things like composite materials with very heavy things like metals, and so we can make new materials in space. We can also make perfectly spherical materials, and the commercial industry is very interested in that. So there are a lot of things you can do with material science in space that you can't do on the Earth, again, because of the absence of gravity. So this is my first mission, was a space laboratory, as I said. Let's see if I can get this to work. This is a different format than So this laboratory is in the back of the space shuttle. It has a long tunnel that you sort of fly down like Superman to go to work. And so this laboratory is much like the laboratories we have on the International Space Station. And it's just full of experiments on the sides, in the racks, in the ceiling, in the floor, down the middle, in the aisleway. There's just tremendous volume for experiments. And so the space lab missions were actually precursors to the space station that we have now. So we learned a lot of science, did a lot of science. My mission was a mission with the Japanese, so we were able to do a lot of experiments with the Japanese scientists. This is one of them. This is actually one of the material science experiments where I talked about melting the metal so that we can understand how it melts and what it does. This happens to be glass, so they were trying to understand how glasses melt and how we can form them and how we can understand the fluid physics of molten glass. Let's see. There we go. So this is another material science experiment that I did on my first mission. And have any of you heard of the material samarskite? It's not a real commonly known material, but those of you who understand thermodynamic equilibrium diagrams and how you have to create those to really understand a material, well, this material was so difficult to work with on the Earth with gravity that they couldn't get these very fundamental characteristics of the material. So we put it in this furnace in order to melt it, in order to get the characteristics that they needed to make these very basic diagrams. So this furnace is kind of cool because it has 2 hot chambers and 2 cold chambers, and so it's continuously heating, so you don't have to turn it on and off to change samples. You just rotate the cold sample into the hot sample chamber and then the hot ones into the cold ones to cool off. And so you're continuously heating the furnace, and we actually have this on International Space Station right now. So this was my second mission, and this was also a scientific mission. It was a smaller habitation module than the Space Lab. It was an extension of the middeck, which is the crew compartment, the downstairs part of the crew compartment, where we did a lot of experiments. So the Space Hab created another volume where we could do more experiments. So this is actually the one from my second flight, and that's me on the left with Franklin Chang Diaz. And so we're going into the Space Hab and getting ready to turn everything on and start our experiments. And we had about 14 extra experiments with this extra space. So again, a great laboratory, not as big as a space lab, but you can see there was still quite a bit of capability that we had that we could use to do more science. Sorry, this is different than there we go. So people ask me what my favorite thing to do in space was, and other than look out the window, and especially when we flew over Huntsville, my hometown, this experiment was my favorite. It's called protein crystal growth, and this is the biotechnology part. So your body is made up of proteins, protein crystals, and sometimes we don't know what the structure of that protein might be. And just as I said, when you grow things in space, you don't have to have a container. You don't have to worry about gravity making something bombard the material or the crystal that you're trying to grow. So we can, this is an example on the screen of earth-grown crystals and space-grown crystals. The crystal that I'm trying to grow in this experiment looks just like a laptop, but it's hooked up to some big canisters filled with solution that contain insulin. So in 1994, we didn't know what the structure of insulin looked like. But by growing it in space, we could grow it much better, and we were able to get a perfect crystal of insulin. So they take this crystal, when we bring it down to Earth, they have X-ray diffraction machines that can create in a computer model what that crystal looks like. So when you have a crystal in a 3D model on the computer, and some of you folks who are doing a lot of programming and things like that, you can imagine if you have a 3D model of a crystal, of a protein, you can see the sites where bad bugs might attach. But the pharmaceutical industry is very interested in putting a pharmaceutical where that site might be to keep the bad bug from attaching. So that's another application of protein crystal growth. In this case, the insulin was just to find out what insulin really looked like. So this was a huge breakthrough in 1994 that they were able to determine what insulin really looked like. So it was a very proud moment for me. The other thing is, I was supposed to be going to bed about that time. About the time my crystal started growing, I was supposed to change some things on my laptop to make it grow, and I was supposed to go to bed. And they were the ground was trying to get me to go to bed, and I'm like, no, I can't go to bed. I gotta grow my crystal. So I was really happy. This is a happy face because my crystal was growing. Another thing we use in space to help make our discoveries is robotics. You know, the combination of the human and robotics are a great combination to do things in space. So on this flight, I know it's hard to see, but in front of the payload, there's a kind of twisted, there's an arm that's about 6 feet long. And so that was an arm that we were flying and I was operating that was going to be the Japanese fine arm, which is now in the International Space Station. So this arm could do things like turn a doorknob. It could take an experiment from a pallet and put it in the module, you know, so you don't have to send a person outside to get the experiment. So we were able to test that on my third mission. We also wanted to check out how you could operate this without cameras, because we knew at the time this was going to be used. We weren't going to have cameras or windows looking at what we were operating. We're only going to have cameras. So we were trying to do it without looking out the window and only using our cameras. So we did a lot of technology development and robotics development on this flight, getting ready for International Space Station. I also did robotics with the Canadian arm, which is operated with 2 hand controllers. And so it's not really robotic in the sense that it flies on its own. You're operating it with 2 hand controllers, 1 translation, 1 rotation, to move this arm around, to get it to grab onto something with its grapple fixture, and then to let go. So this next video shows you the Christospaz satellite, which I deployed on my last mission with the Canadian arm. This video is actually of the first time it flew, not the time it flew on my mission, but it's the same satellite. So here comes the arm. We put the grapple fixture, the grapple around the grapple fixture. We lift it up out of the payload bay and very carefully move the arm away from the satellite. This particular satellite is called Christospaz, which looked at the ozone levels at different altitudes as it orbited the Earth. So this was used back in those days to correlate the ozone levels with the computer models that the meteorologists had and the scientists had. So we had it up there for 9 days on my mission. So that's really all I wanted to talk about with the space shuttle and with my flights. Those are just some examples of the type of science we did and why humans go to space and why we go to space to advance discovery. So the next thing that I worked on as a professional after I left the office was I came back to Marshall and we worked on the technology and hardware and operations. We do all the science operations here in Huntsville for the International Space Station, and that was what I did after I left the astronaut office, was set all that up. So here's a picture of what the International Space Station looks like today with the assembly complete, is what they call it. So it's completely put together. You can see the different modules on here. You can barely see the Japanese fine arm on the upper. The upper module is the Japanese module, and the arm to the left is the Japanese arm that I worked with on my third flight. So I'm curious, and I have a prize here. I have a USB thumb drive. It doesn't have much memory, so don't get excited. But it does have my logo on it and my name. And you have to raise your hand. Who can tell me how many people are on the International Space Station right now? Raise your hand. Yes? How many? No, not 8. Yes, in the front? 6 is correct. So you can come up later and get this. Okay. Oh, okay. Or you can come down. All right. 6 people are on the International Space Station right now. You know how I know? There's an app for that. There's an app called How Many People Are in Space Right Now? And what does that say? 6. So it also gives you their names and pictures that they took. So it's a great app. So the next quiz question is, and for this one, I have a pin of the Space Launch System, which I'm going to talk about in a minute. So who can tell me how many women are on the International Space Station right now? There's a lady right there who raised her hand. How many? 2 is correct. Yay. And what's significant about those 2 women? What did they do Friday? The first all-female spacewalk. So it's very cool. Christina and Jessica, yeah. Okay, so now we have the International Space Station where we have people in space even longer than I had on my flight. You know, my flights were 8 days and 12 days, 2 12, 1 8 day. And so now we're up there all the time, and we've been up there since 2000. We've had people up there continuously doing science since 2000, which is fantastic. So we can do even more science, as you can imagine. And the other thing about it is we are what we are calling Earth reliant. So we're developing technology, but we're still dependent on the Earth. We're still dependent on, you know, all kinds of materials coming up, spare parts, clothes, food, water. So on the right is, those are bags of water, which is expensive to fly. Now, we do have a capability with the environmental control system to generate water, drinking water, out of urine, out of sweat, out of condensate, but we have to make sure we have enough water so we don't rely on that. We can't rely on that 100%. We have filters that we have to replace and then, you know, throw the filters away. We have samples of our experiments and those kinds of things that we have to return to Earth, and environmental samples. In other words, you know, measuring microbes and things like that, and different constituents on board the International Space Station, we have to send those back down on the vehicles that come back down. Look at the replacement equipment. That's part of the environmental control system, the distillation assembly. It's a big piece of equipment. The EVA we talked about, the spacewalk, was to replace some power units and power charge and discharge units on the International Space Station. So we still have to send those parts up. So we're still Earth reliant, even though we're doing some remarkable things. The other thing we're doing on the International Space Station is we're developing technology for the next step, which is what we're going to talk about. So this is Earth reliant, I talked about. The next step is exploration. Discovery, that's what we're doing now. We're discovering, we're learning, but we're going to explore even further. Exploring new places we haven't been before, in new ways that we haven't done them before. So that's why we go to space also, to discover, but also to explore. And we're going to do that with the Space Launch System that I mentioned, the next rocket that we'll be launching. The orange in the middle is, again, liquid oxygen, liquid hydrogen fuel tanks that will power the engines that are on the bottom. So the engines on the bottom, there are 4 of them. On the space shuttle, we had 3, but the leftover engines that we had from space shuttle, because they were reusable, so we still have them, we're going to put 4 on each Space Launch System rocket that we build. And then on the sides are the solid rocket boosters, which look a lot like the ones we had on the space shuttle, and that's because they are the same, except they have 5 segments instead of 4, so a little bit bigger. So a little bit different configuration for the boosters. Those are ready to go. They're ready to go. They're in Utah, ready to go to the Cape to integrate. On the top is bigger than the Apollo capsule. It can carry 4 to 6 people. The first time we carry a crew, it'll have 4 people. And so this is the next rocket that NASA's building. The core stage, which is the orange part that has the fuel tanks, and the engines at the bottom are being put together right now as we speak at Michoud facility down near New Orleans. So those are going to be shipped to a test at Stennis Space Center in Mississippi, and they're going to fire the whole thing. The fuel tank feeding the 4 engines, and they'll do a full flight duration. Big test. So the core stage will be delivered in December, and then we'll test it next year. So that's the Space Launch System. And with the Space Launch System, we'll be able to explore further than people have ever before. And so it's very exciting to be a part of that and to know that we're a part of this new exploration and these new that we're. So I'm sure Lisa talked about Artemis 1, which is the first time we fly SLS without a crew in 2020. So we'll be circling the moon and going past the moon farther than we've ever taken a vehicle like this, and then come back. And then Artemis 2 will have 4 crew on it, and it will also go moon. Then what Lisa talked about probably is the human landing system, which is part of Gateway. So we'll have an orbiting Gateway module and propulsion module, and then a lander. And the lander will go down to the moon, and then we're able to stay longer. We're able to do more things and explore more. And different parts, as you heard, one of the teams talked about the places that we're going on the moon are different than the places that we've been before. So it's all about exploring. So we call the moon the proving ground. So the proving ground, we're, a few days away from the Earth, but we can really figure out how Mars, what kind of technologies we're going to need to go to Mars. So instead of filters that we just throw away, we have filters that we can reuse. We have to think about how we can increase our use of consumables, not just urine, but maybe some other things. How can we use that? And how can we analyze things on board without having to send them back to the Earth? And how can we repair equipment in space without having to send spares up or send, different ways of fixing whatever it is that's broken? We can use 3D printing. We can generate, things on our own from what we have on the gateway. So it's really a proving ground. We're too far away, really, to just go back and forth to the Earth when we need something. We're going to have to be able to do some of those things ourselves on the moon. So that's what we call the proving ground with the crewed missions, the deep space hardware. The Space Launch System will take us there. And then after that, we might be ready to go to Mars. And that's where we need your help, because that is Earth independent. It's a 3-year round trip. We can't even, be like the proving ground where we're a few days away from the moon. We're, many months away. So we have to be totally independent. How are we going to protect against radiation? How are we going to have food? How are we going to have water? How are we going to sustain life? Those are the kinds of problems that you need to help us solve. And we'll solve it by going to the moon. We're station first, Earth reliant, the moon, the proving ground, so that we can be independent. But we have to figure out those technologies before we can send people to Mars. So we'll have to figure out how to make equipment up there, maybe use the Mars resources for food or to, materials to make things. How can we make a habitat up there? How are we going to protect ourselves against radiation up there? How are we going to have consumables? How are we going to analyze things? How are we going to communicate with a 20-second lapse? So that's Earth independent, and that's the kind of thing that we need to figure out when we go to Mars, and when you go to Mars, when we send people to Mars. So we've sent robots, which is great. We've learned a lot, but we need to do all these other technologies and these stepping stones, and you need to help us figure out these challenges that we have before we can send people to Mars. So why do we send humans to space? Discovery, exploration, inspiration. We want to inspire the next generation. We want to inspire you. We want you to be motivated to help us solve these challenges for the future. And leadership. That's what we do in this country. We have the leadership to provide the capability to send people into space, which is an incredible asset that we have in this country when we have international cooperation. So it's, in my opinion, after looking at the Earth from space, and you see that one home, I think that's a way for unity and for people to get along, is to work on these missions to space. So if you want more information about those, here are some websites. I don't have the the Human Landing System or Gateway, but it's up there with the SLS and Orion. Orion is the name of the crew capsule on top. So that's how you can keep up with what NASA's doing and how we're paving this path to go to Mars. Some of you would like to go to Mars. I would, actually. And then here's some information on me also. If you're interested, I have a Facebook page and a website, Twitter handle. And so those are ways to get in touch with me or learn more about what I'm doing these days. I work for Bastion Technologies, which is a NASA contractor, so I still love supporting the NASA missions, and we're helping to build the SLS. So thank you so much for your attention. I appreciate the invitation to come. Thank you.
Thank you so much, Dr. Davis. Thank you very much. That was awesome. What a great view into the future. Before we get to go further along, you'll notice there's been some space bling coming on and off here, and we got to hear from Andrew Denio about what the Space Bling is about. Andrew.
Thank you. Thank you, Jan, for your. I had to follow an astronaut, so I have a lot to live up to. But I just wanted to kind of talk about the trophies this year. I wanted to thank Urban Engine and Steamworks for sponsoring the trophies this year. By the way, it's hashtag Sore Throat Challenge this weekend, so I hope you get on that. So last year, you might have seen the trophies. I thought they were kind of cool. This year, I want to do something different. I got really into sort of the PCB life. You can check, and wanted to make these PCB trophies. You can see the bling up here. This is more of a talk for the struggles that I went through, and also for the winners tonight to know that how to interact with these and how to hack them too. Everything's sort of based on the Arduino environment, and mostly everything contains Adafruit devices. There's 2 power switches, so one of the things that I learned was that I needed to sort of wire this differently, because I ended up needing to put 2 power switches on it. So one's on the back, one's on the battery, FYI. When you get to the home screen, when you cycle power, you'll see what the buttons do. It'll tell you press 1 to scroll up, 2 to scroll down, 3 for select, 4 to main menu. So in the main menu, we have 5 categories. We have NeoPixels, which are these little LEDs. We have a light sensor, so I'm gonna go up to the light sensor. I'm gonna hit select. It's gonna load. And there's a little light sensor here that tells you the sort of the intensity of the light, and it's displaying it on the display below. So if you get it brighter or darker, it'll change that value. To go back, you just hit the menu button. There's also a temperature sensor. There's an accelerometer, so you can measure the different G-forces in the X, Y, and Z direction. And yeah, I just want to say also these 3D bases are kind of loose, so just kind of, when you pick them up, make sure you put a hand underneath. I got the hardware done last week. It's been months of development. This is almost my first PCB design. So luckily everything sort of works. And what was I going to say? Yeah, so hardware was done last week. Didn't really get too much of the software because I was also like part of the organizing committee trying to get this event running. And I really just started the software yesterday. So you guys might have seen me in the lobby. Everyone kept commenting like, oh, you got your own like little personal hackathon going on. I was really trying to make these things work before the award ceremony today. And I got finished at 2:30, so I was really happy about that. Thanks. So each one's kind of labeled. Let me just talk about the components real quick. On the front, you have a e-ink display. It's what you'd see on a Kindle. So when you power this off, whatever's on the screen still stays. You have an alphanumeric display down here, as you saw. You have these NeoPixels, some buttons. On the back, you have the brains, which is a Adafruit Feather 32U4. You have a temperature sensor, an accelerometer, and then you have a little prototyping board. So you can solder your own components on there and make it happen. There's a GitHub link on the back. Haven't had time to put up the information yet, but if you go on there later, I'll put all the code up there and like how to use this thing. Part of the struggle too was I picked this board because it's sort of like a low barrier to entry. It's almost like an introduction Arduino board. So I thought I'm not going to pick like something complicated that you have to go learn a lot of code for. You can just get it right into it. However, one of the limitations was I only had 28 kilobytes of memory to put on here. Usually that's not too much of a problem. Sometimes you don't really use all that space, but I have 6 bytes left in this program. So it's like I kept, every time I compiled it, it would be like 101%. I'm like, so I had to like keep like finding ways to like combine functions and like change an integer type into a byte type to save just a little bit of space. So it was like a huge learning process, and so I'm really glad it happened. There's a space on the back where you can like write your team name and stuff. So every team will get one of these. When you come up on stage, you'll pick up your trophy, And then you're going to go over here. Everyone has a non-blinged out medal that looks something like this, different colors for different awards. Even though it doesn't have all the bling on it and everything, it has everything ready to go where if you want to make it bling, there's a GitHub link on the back. Again, haven't had time to put all the information yet, but I'll do that this week. I'll tell you like what components you need to buy from where, and you can solder everything on yourself and upload code and make it work. So yeah, I just want to thank Urban Engine, and I really had my ambitions high, and I needed just a little bit more money, and I reached out to Mike Murdoch, and I was like, hey, I just need a little bit more money to make these things really cool, and he was like, here you go. So I just want to thank Mike Murdoch for making this happen, and Urban Engine. And yeah, so now we're going to hear from Mike. He's the founder of Steamworks, the local makerspace in Huntsville. And take it away. Thank you.
Thank you. So being the next speaker after Dr. Davis makes me understand how it followed Elvelt. So last year I talked about lessons we could learn from failure. This year, since I have experience in failure and success, quite a bit, especially on the failure side, I thought I'd talk about what we can learn about from successes there. How many people do we have that participated in space apps in the audience? Oh, great. And how many of you felt that you had some success, whether you won a prize or not, that you had success space apps? Okay, so right now, let's just take a moment to bask in that glory quietly. It's okay to go, oh yeah, for just a second. Okay, that's enough. We don't want you to rest on your laurels. That's a kind of a funny phrase, rest on your laurels. It comes from the Romans a couple thousand years ago. They used to honor great generals and statesmen by making wreaths out of laurel leaves and putting them on their heads. We can still get laurel leaves today, although they're not as honored as they were. You can find them in the spice aisle in the Publix. They're called bay leaves. Put them in your spaghetti sauce, and then when you eat it, you fish them out and put it on the side of your plate. So not quite the same. That's why we don't say, don't rest on your bay leaves. But resting on your laurels means just coasting on successes you've had in the past without getting any new successes. So we don't want to do that. We want to move forward from our successes. And the best way to do that is to analyze, to spend the time and put the work in to figure out why we were successful, what worked on there, how we can emulate that. There's a saying that nothing succeeds like success. And I like to think that the word succeeds doesn't just mean succeed as in being successful. I think it also means to follow, as in succession. So, because you'll find that once you have one success, then the next success becomes that much easier. And you can talk to serial entrepreneurs or very successful people, and they'll tell you the same thing. So, of course, within successes, we're going to have some failures. And we need to look at those failures, too, with the same kind of analysis, so we don't repeat those same mistakes, so we can see maybe how those failures shaped our success, how they led us down the path. In fact, two of the greatest inventions I know were discovered by accident. These are inventions that changed civilization as we know it. They were penicillin and Post-it notes. So, both discovered by accident. So if you have an accidental success, then you actually have even more work to do, because you may not know how you got exactly where you ended up, and you need to do some more analysis to see what happened there. But one of the ways you can make it more likely to have an accidental success is to be open to new ideas. Now, the tricky part is you have to balance that with a relentless drive for your original goal with being accepting of a new goal, something you weren't expecting to find. So that can be tricky sometimes, but I think you'll find that keeping an open mind while you're doing the work can be very successful. So success gives us some new perspective, and you can use that perspective to understand and emulate the success of others. So there's a lot of lessons we can learn from success. it's worth it to put in the work and maximize your learning from the experience on there. And whatever you do, nobody leaves.
Thank you, Mike. Matt, gonna roll the video?
You introduce?
Let's roll it.
All right. I don't know what happened to the sound. All right, well.
I'm Jim Green, the NASA Chief Scientist, here to thank you for all the hard work that you did in the Space Apps 2019 Challenge. What a fantastic set of topics that you went into. We studied the Earth, our oceans, the stars, and into the solar system and how we want to work and live on Earth. Fantastic topics. Thanks again for your participation. I want to take this opportunity to thank particularly the local leads, those people in these locations that really helped the organization and helped you along to your challenge. Thank them very much. One of the things you learned in your Space Apps 2019 challenge, I'm sure, is that you had to work well together in teams. This is something NASA does every day. Learn to work on teams to accomplish major scientific and exploration activities that you can't do individually. Space Apps 2019 was a fantastic event with more than 200 locations participating in 80 countries. Can you imagine that? Let me take this opportunity to tell you some of the exciting things that NASA's up to now. It's called the Artemis program. This particular program is developing the Space Launch System with the Orion capsule, capable to take astronauts to the moon. And in 2024, we'll have the first woman and the next man to walk on the surface of the moon. 2020 is going to be an amazing year for NASA. In July of 2020, the road to Mars opens up, and we're going to launch a rover about the size of Curiosity and be able to core rock, create samples that we're planning to bring back. Also in 2020, we're planning on launching the Space Launch System with the Orion capsule. Now it will be uncrewed, but we'll have the opportunity to orbit the moon, come back, and study everything about how that system works before we launch humans, which will be the next step. You know, also in 2020, we're making major progress getting James Webb Space Telescope ready to launch. It is so huge, we're going to be able to look out towards the beginning of the universe. Pretty spectacular. So over the next several years, we're going to continue to launch spacecraft out into the solar system and also studying our planet. This is a fabulous time because we're going to accumulate more data, so get ready for the next Space Apps 2020 challenge announced soon.
Okay, I need Jim Green's energy. That guy's amazing. Anyway, we've got some awards to give. Anybody wants some awards? That's kind of a weak. I want to hear more applause for the awards. I want to hear more energy from you guys. Yeah. So first, for Space Apps Huntsville, we have the best use of creativity, which is awarded to the team that demonstrates the ability to think outside the box. Although in this group, the box doesn't seem appropriate, does it? It's almost like to think outside the galaxy. So anyway, without further ado, the dream team for best use of creativity. Come on up. Okay, you're gonna hand out the. Put the laurels on.
Congratulations. Thank you.
Let's hear it for best use of creativity, the Dream Team. Okay, you go that way. Congratulations. For the champions of innovation, it's awarded to the team who presents the greatest innovative solution. The Cyber Sisters. Come on up. I want to thank the Academy.
I'd like to thank this trophy for being so cool.
I think the Cyber Sisters would like to thank the trophy. Who named you, ladies? I love your name, so congratulations to you. So the Mentor Award is awarded to the team who's endured given significant obstacles presented throughout the competition. Lean forward, fail smart, bear people.
Just a little housekeeping notes for everyone who's winning tonight. After this is all done, make sure you come over here. We need to get your information, email addresses, phones, names to mail your, we need to email you your I-9s so you can get your checks. Thanks.
Thank you, Ian.
Here's your trophy.
This is very, very good. The Bear People. And last, the best display of teamwork is awarded to the team who demonstrates high morale and whose solution demonstrates full participation and collaboration between its members. Hypernova Studios, come on up. It's hard putting laurels on, isn't it?
Here's your trophy.
All right, Hypernova Studios, let's hear it. I think we've got something else to do, don't we? I think we have some finalists and some winners in the high school division. In second place, Cyber Sisters, come on back up. Excellent. By the way, that check is very difficult to get into the ATM machine to deposit. So Sierra will give you the instructions how to do that. For the high school division in first place, let's hear it for forensics. Excellent. Congratulations. In the open division, in second place, we have populated risk. Come on up. Look at Emily.
Thank you.
And last in first place, we have Starstruck. Congratulations. Congratulations. Great job.
Okay. Good? Not good?
Hold on.
They're starstruck.
I mean, Jan's here. I'm even Jan Davis. All right.
Did you get it? Okay. Now I think, Sierra, we're still going to have photos beside the Saturn V outside. Is that right, or no? Nope. Nope. Okay, that's it. All right. Do we have a closing song? Do we have a closing rap? Anything? I think I'm too tired to do that, but I want to say thank you. It was an honor and a privilege to be with you this weekend. Thank everyone who participated. Thank the sponsors. Thank Booz Allen, NASA, everybody who believes that our future is in this room and around the world to solve our future problems and to give us future solutions. Thank you each so much. Have a wonderful evening and good night.